Hello, I'm Vahid Lotfi and I'm an Emeritus Professor of Management Science. In this video, I'm going to show you how to conduct nonlinear regression using Microsoft Excel. So let's get started. For this demonstration, I will use a nonlinear function to generate a dataset and then use the dataset to demonstrate how to do nonlinear regression. The function that I have selected for the purpose of demonstration is f of x equal to 10 minus 5 minus x to the power of 3, that when you expand is equal to x to the third minus 15x squared plus 75x minus 115. So let's use this function to generate the actual y values. I've selected an arbitrary set of x values. So the actual y value in the first one is going to be equal to 10 minus parentheses 5 minus the x value raised to the power of 3. And I can just copy this formula down all the way to the last data point, and these will be my y values. Now, ordinarily, you will not know the form of the function and you have a set of data that you would like to use regression in order to develop the formula and possibly predict the future. The first step in doing regression is to actually plot the data so that you can see the shape of the function. So I will highlight my data and select insert and select scatter plot, and I'll just take a line like that. And I'm going to move this plot over here because I am going to add additional plots as we move forward. As you can see, the shape of this data set or the hypothesized function is clearly not linear. So if I do linear regression, I am not going to get very good results. So let's start by doing simple linear regression and see how that line is going to look like and what kind of a strength we are going to get. To start, I will go ahead and click on data and then data analysis and select regression. Click OK. I'm going to have to input my y range, which is over here, and then my x range, which is over here, and notice that I have to check mark the label because I included the label, and then I have to select an output range, which I am going to select this area here as I will continue to do more regressions, and then I'll just click OK. So I get my regression output, which is in the form of an analysis of variance table or the ANOVA table. The first thing we want to do is to look at the ANOVA table and in the regression line and see the F statistic and the result of this F statistic and see if it's significant. In this case, the p-value is 0.000795, which is obviously less than 0.01 or 0.05. Therefore, the regression model is statistically significant. The next thing we may want to do is to look at the R-squared value in the regression statistics, and in this case, the R-squared value is 0.77359, which is about 77.3%. The R-squared value describes the percentage of variation in the dependent variable or y values as explained by the independent or the x value. And then we can look at the regression function equation. The intercept is minus 883.8 the coefficient of x is 165, therefore the linear regression function equation, or the estimated one, is f of x equal to minus 883.8 plus 165 times x. I'm going to use the regression function equation to predict the y values and then plot the line. So for that purpose, I'll put predicted here, or this is going to be y, and I'll just call it linear, and put the formula in there, and this is going to be equal to the intercept, which is right here. We'll make sure that it's an absolute value, plus the coefficient, which is here. Again, we make sure that it's in absolute value sense, multiplied to the x value, which is here. And that is going to give me the predicted value for x equal to 1 based on linear regression. I'm going to just copy this formula down here, reduce the number of decimal places a little bit, and then enlarge it. Okay. Now we are going to plot this line against the data and compare it with the actual observed values. For that purpose, I am going to highlight the data and then insert. As usual, I'm going to take a scatter plot and a line, and there we are. Let me move this graph down here below the first one. We can see that the linear regression line goes through the data, but it is not a perfect match with the actual observed values, which is nonlinear. So we should be able to do better. Next, I'll hypothesize that my curve is actually quadratic, which is to the power of 2, x to the power of 2. So let's take a look at that and see how we can accomplish that. I'm going to move these two columns, one column to the right, to make space for x squared, because that's going to be the x squared values. So the x squared values will take this, raise it to the power of 2, and copy the formula, and now I have my x squared values. So I'll go ahead and do another regression, this time using two independent variables. So again, we click on data, data analysis, regression, click OK. Select the y values, select the x values, now select a place to put the regression output. I'll put it below the first one and click OK. So here we have the results of our quadratic function. Let's take a look at the p-value again. You can see that the p-value is much smaller than the p-value for the linear relationship. Let's take a look at the r squared. The r squared in this case is going to be 0.982 or 98.2% compared to the r squared in the linear model, which was 0.77. And then of course we have our regression function equation, which is 346.29 as intercept plus minus 191.17 times x plus 16.64 times x squared. Next, we look at the p-values for the intercept, the x variable, and x squared, and all three p-values are small. The p-value for intercept is about 0.09, which is insignificant, and we can ignore it. It won't hurt anything if you include the intercept. But the p-values for the x and x to the power of 2 are extremely small, meaning the variables are significant. And we are going to use this regression function equation to do the prediction again. So I'll go back up to the data and put quadratic here. Let me widen the column a little bit. Okay, and I'm going to start putting the formula here. And the first thing is the intercept, which was down here, and we make this an absolute cell reference, plus the coefficient of x1, which is here, and I'll make that an absolute cell reference, multiply to x plus the coefficient of x squared, which was down here, again absolute cell reference, and that is multiplied to x squared, which is in this cell, and that's my formula, and we get 177 as the predicted value for x equal to 1. And we'll just copy the formula down here, and these are our predicted values based on a quadratic function. Next, I am going to show the graph. I will use this area to temporarily store my data so that I can do the graphing, starting by copying the x values. And I'll do paste value, okay, followed by actual linear and quadratic. So I'll just make a copy and place the cursor here and just select. Now I can graph the data, and I'll have the x value, the actual, the linear, and quadratic. So we're going to highlight the data and then insert, same thing, a scatter plot, and we have our chart, and I'm going to move this chart below the other two so that we can compare them. So let's take a look at this chart. So the blue line is the original data or the actual, you can see that. The orange color line is the linear regression fit, and the gray line is the quadratic regression function equation. And you can see that the gray line, which is the quadratic function, traces or follows the actual observed values much closer than the linear regression line. At this point, we can just stop the analysis because we do not know the actual true relationship or functional relationship between the dependent and the independent variable, and the quadratic function fit pretty well. However, for the purpose of demonstration, I am going to add another term, which is x to the power of 3, to show you that you can continue exploring more and more powers of the independent variable and see if there is any significant improvement. So again, let me move this data to the side. And here I'll have x to the power of 3. I'll just call it x3. and this is going to be equal to Rx to the power of 3. And as usual, I'll go ahead and copy the formula and enlarge the x values. Okay, and now I can go ahead and do another regression analysis and include the x to the power of 3. So we'll go ahead and click on data, and we go to analysis. As before, we select regression, we select the y values, we select the x values, and we select a region to place the output. And here we have our regression results. Once again, we can see that the p-value for the regression analysis is extremely small, almost near 0, which indicates that the regression function or estimate is statistically significant. Look at the R squared. It's 1 or 100%. Well, why? Because I had actually generated the data using the nonlinear function with a power of 3. And I didn't include an error term. And we look at the regression function equation is minus 115 plus 75x minus 15x squared plus x to the power of 3. Let's compare this with the original equation. Voila. Minus 115, 75x minus 15x squared plus x to the power of 3. It actually predicted it with 100% accuracy. No surprise. And if I go ahead and use this regression function equation to predict the y values, they're going to be exactly the same as the actual values, but just for the purpose of demonstration I will do that. Here I'll just call this x to the power of 3. I'll just call it power of 3 and start typing the regression function equation, which is going to be equal to our intercept, and I'll make this an absolute cell reference plus the coefficient for x1, which was 75, make it an absolute cell reference, multiply to x plus the coefficient for x2 or x to the power of 2, absolute cell reference, multiply to x2 plus the coefficient for x3 or x to the power of 3, multiply to x to the power of 3, and that is our value. And notice it became as minus 54, which was the actual value. And if I just copy this cell down, we are going to get exactly the same as the actual values. I don't need to plot this because it's going to overlap with the actual observed values. You can continue and use the power of x4, x5, x6, etc. as long as your R squared is small, or you want to improve the regression function equation. And that is how we conduct nonlinear regression using Microsoft Excel.